All right, now we can start. Welcome back, everyone. Hopefully you had a really good week. All right, so what are we learning today? Today we're going to do an introduction to functions. I know some of you heard before, like Aiden, yeah, who does coding. Functions is a big topic in coding, but we're going to look at the mathematical side of functions. Oh, you've probably heard of this. So, oh, there's Selena. I'm just missing two people. That's all right. Okay, without further ado, let's get started. So let's get an introduction. Like, what is a function? Of course, for those of you who have never heard of this. So a function, basically, it's a process for turning a set of inputs into outputs. So think of like this function machine right here. If you see the middle picture, use a pointer. This one. So you have the inputs in here. It goes into the machine. So you have spheres going to the machine, and the outputs are these. These look like cubes, but some of them look like rectangular prisms. So when your inputs are these spheres, your outputs are these rectangular prisms. So that's what a function does. It converts something into something else. Yeah. And this is a special feature of a function. So each input only maps to one specific output. So what does that mean? It means that for each input, you only get one specific output out of that. You can't, if you get two, that means it's not a function anymore. And what does this look like graphically? Like on a graph? A graph means that this passes the vertical line test. What's the vertical line test? So you run a vertical line through any point on the graph. And if it crosses more than 2 points, like the circle, or sorry, more than 1 point. So if it crosses 2 points, like the circle, that means the graph is not a function. So you see a circle is not a function because the vertical line test passes through it twice, while the vertical line test on the right side, so this function right here, this function is I just call it's a function. So yeah, because it only crosses through it once. So you have an input right here, it only maps to this one output. Like for a circle, if you had say 0, 0, 0, if you put x equals 0, you'd have this output and also this output. So you can't have two or more outputs for one input. That's what it means. And also let's go over function notation, right? This is important. So look at this image right here. You can see that you have this f, and in brackets you have x. What is that? So f is the name of your function. Name of function is f, and in brackets, this is the input. Whatever you put inside brackets is your input. So the input in this case is x. And it can be anything. It can be x, it could also be like 2x, or it could just be like a simple number, like here, 2 or -4. And what this is, so it's 3x plus 1, that's like your equation, your output. They call it your, we'll look at domain range in the next slide. But so this is your output of the function, and this is your input of the function. And you can substitute numbers into here to get outputs. So like say f at 2, or they call it f of 2, but you can also say f at 2. So let's call it f at 2 equals 3, and then you substitute 2 into the x. So 3 times 2 plus 1 gives you 7. Same thing for -4, you would get 11 in this case. -11, I think. Yeah, they made a typo here. It should be -11. All right. Any questions about this before we move on? Any questions about these functions? Sorry, any questions about the definition? Hopefully you all understand what this is. Very straightforward. Okay. Oh, here's the principle. All right, 金老师好. Okay, so now let's go to the next slide. So let's cover domain range. So it was in this picture. They call it input the domain, the output the range. What does these mean? Okay, so domain range. Let's look at the domain first. Domain is the set of all possible x values that a function can take. All right, so like this is basically a set of like whatever. So whatever you put in here, that's the domain. So the input, so the x right here, that's part of the domain. So all the possible like values that you can put inside the input is right here. That will make your domain. Now the range is a set of all possible y values that a function can output. So if you gather like your domain and you for each of those values in the domain, you take you run the function for them, then the range is like the set of all of those all the possible like outputs that you get from doing that process. So all possible y values that you can output. And let's look at a couple examples. So let's look at this left example. So we see that it has a diagram of like a domain of like A, B, C, D, and each of these point to like an element in the range. So A points to I. Well, this is the Roman numerals for 1, and B points to 2, C points to 3, and then D points to 4. So how would you write your domain range in this case? You'd use a set notation, and you just put all the elements inside that set. So for a domain, you would have in your set you have A, comma B, C, and D. That's your domain. It's just all of these values right here. And your range is just all of your values over here on the right side, which is 1, 2, 3, and 4. So that's domain range for this. So that's for a table or anything, or like where you have all the values that are mapped. But what if you have like a function? Say you have f of x is equal to x. So you want to find domain range of that. So domain, this is pretty straightforward. It's x belongs to a set of real numbers. This is what this means. So what this means is basically like x can be any value that's a real number. Yeah, so this e right here, it just means belongs to the set of. And the R here just stands for real numbers. So this is what that notation means. So domain is x belongs to a set of all real numbers. And same thing for the range as well. So you write, instead of x, you write y, and y belongs to a set of all real numbers as well. So if you like think about the graph of f of x is equal to x, if you've seen it before, it's just a straight line, right? And it like goes all the way to like infinity, negative infinity, like from the x side and from the y side. So that's why you have this domain range. And there's like no breaks in between, right? It's a continuous line. So yeah, it covers like basically all the x values and y values that you can graph. Any questions about this? Okay, if there are no questions, let's do a couple problems. So here, for each of the following questions, find the domain range and determine if it is a function or not. So you want to find domain range, and what this means to determine if it's a function or not. Remember, the definition for a function is that each input only maps to one specific output. So you have an input. If you have an input that gets to two outputs, then your graph is not a function. All right. I'll give you guys a minute to solve these. All right. I think it's time to take it up. Okay, let's look at the first question. Can someone tell me what the domain and range is for the first question? So what's the domain? You can type in the chat if you want to, or unmute yourself. Does anyone have an answer for a first question? 1, 2, 3, 5. Yeah, you just take all the x values. That's your domain. What about the range? Oh yeah, just a thing. You always want to put your values in numerical order from like these increasing order. Like say you have a range of like 5, 4, 3, 2, you want to rearrange it to 2, 3, 4, 5. Mhm. So what's the range? Yeah, 5, 5, 10, 15. All right. Yeah, I think you repeat the 5. I'm not sure if you repeat the 5. Let me just double check actually. I don't think you can have repeated values in the range. Let me check. Um, okay. Yeah, so I forgot to mention this. So if you have a repeated value, it doesn't matter if it's the X or Y. If you have a repeated value, you don't have to list it twice. You just list it once. So it'd just be 5, 10, 15 range. Make sure you put those squiggly brackets around it so you know it's a set. Like that, what I typed in chat. And is it a function or not? Can someone tell me? Just say yes or no. Is it a function? Or question one? Yes. So pick one. No. As I said, it is a function. Just because even though like you have repeating y's, you see that each of these x's they map to one output, right? One maps to 5. It doesn't map to anything else, right? 2 also maps to 5, but it doesn't mean that. But 2 also doesn't map to anything else. 3 goes to 10, doesn't go to anything else, and 5 also goes to 15, nothing else. So therefore, it is a function in this case. Yeah. Okay, let's look at question 2. What's the domain and range for question 2? Just type in the chat. And remember, no repeating values. And also make sure to put it in increasing order, which I think they are. Yeah, they're in increasing order already. So yeah, -3, -2, -1. That's your domain. What about the range? What about range? What's the range for question 2? Can someone tell me? Yeah, 4, 10, 12, 20. Just take those values. All right, is it a function or not? Wrong again, Bob. It's actually not a function. We'll see why. So you see -3 goes to 4. That's fine. -3 doesn't go to anything else. -2 goes to 10. It doesn't go to anything else, right? Now let's look at -1. You have two -1s. This -1 goes to 12, but -1 can also go to 20. So you see, a -1 goes to 2 values. So that means it is not a function. Sorry, Bob. It's not a function. Yeah, that's okay. It's part of the learning process. Now let's look at question 3. So this is a function. Well, I revealed that, but it's this line, y is equal to 2x minus 19. Can someone tell me what the domain and range for that is? So this time you're not listing out values, you're saying like, where does x belong to? Remember in our previous slide, we had this. So what's the domain range for question 3? Yeah. So x belongs to set of real numbers. So that also y does as well, right? Anything you substitute for x, you'll get any y out of that. If you substitute y for anything, you can always solve for an x. Yes, x fancy ER. You can say that if you want. Okay, question 4. This one's a little bit more tricky. Oh yeah, question 3 is a function, obviously, because all x's go to 1y. So yeah. Question 4. What's the domain for that? Like, can you put in any x? No, it's a function. It is a function. For question 4. Oh yeah, I'll tell you it is a function though. But what's the domain? Can someone tell me? Like, what kind of x values can you substitute into the equation? I'll make it easy. Can you substitute in any x value for y equals x squared? If so, then just write x, it belongs to set of real numbers. What's the domain? Someone tell me. Yeah, same thing. X belongs to real numbers because you can substitute any x and square it, right? You can square anything, any number. So yeah. What about the range? This one's more tricky. Is there a restriction on y? Like what kind of values can y be? And someone tell me. Like think about the graph. Y can be anything. Well, every square, yeah, but like what about the actual like numbers? What integers? Anything can be a square, anyways. You can take square root of, well, not everything, right? So think about that. Like, does y have to be bigger than some number? Like, is there a restriction on y? Someone tell me if there's a restriction on y. Yeah, Aiden got it. It's bigger than zero. Y has to be bigger than zero, but it can also be equal to zero. So the range in this case, the way you write it is that we have this restriction is bigger than zero, right? Bigger or equal to zero. I'll tell you how to write it. So y is equal to zero. I'll type in the chat so you guys can see. This is how you write it. And I'll also go to the whiteboard, just type out for you guys. So basically you put y and then you have a dash. So let me get to the whiteboard. So this is how you write it. So you have y and then you put just a vertical line right there. And next what you do is put your restriction. Your like not the real number one, but like is it bigger than or less than to some number? You put that down. So y is bigger than or equal to zero. You put that down, and then you put a comma. And then after that, you can put your y belongs to a set of real numbers. Because like although y is bigger than zero, but like the y's that are bigger than zero, they're all real numbers, right? So we still have to write this part down. All right. Any questions about this? And yeah, this is a function because x can be anything. Sorry, like x maps to one specific y value, right? When you square an x, you don't get two values, you get one value. Any questions about this? Like this notation might be a bit confusing. So this is y greater than zero. Y belongs to real numbers, and you have to have this y to start. So if there are no questions, let's go back to the slideshow. All right, so let's look at the meat for today's presentation. Let's look at transformations. So you probably heard of these, probably in like, I'm not sure where you learned this at elementary school, but you learn about these transformations sometime. But just to like recap what it is, it's basically the transformation is basically the changes that are used to obtain a new function from its base function. Yeah, so we're defining it now with a function set. So we have this term called base function. What's that? And here's an example. So like y is equal to x. So it's basically like the original function, but without like any coefficients or anything. Or like you don't add any other numbers to it. That's what a base function is. So y is equal to x. You can also have y equals x squared. That's also a base function. Y is x cubed. You have square root x. Those are all base functions. So y equals x is a base function, and a possible transform function would be like you add a 2 to the coefficient, and then you subtract 1 to the whole thing. So y equals 2x minus 1 is a possible transformed function. And there are 4 types of transformations. So you have translations, you're just basically moving the shape to somewhere else, you're shifting it. Dilations, you're increasing or decreasing size, like so. Reflections, so like you're reflecting, well, I have to use the word reflecting there, but like you're basically mirroring it off like a plane. And basically, like, yeah, that's the axis of it's basically symmetrical, right? And then rotations, you basically like flip it around. We're only going to focus on the first 3, so we're going to remove rotations. All right, any questions about this before you move on? So we're going to look at translations, dilations, and reflections. Next few slides. Any questions? Okay, if there are no questions, I'm going to move on to look at translations first. Probably the most straightforward one. So just shifting stuff up and down or left and right. But like, let's look at it in terms of the function. This might be a bit tricky at first, but we'll get the hang of it. You'll get the hang of it. So you have some function f at x, and then you add c to it. C is just any constant number, any real number you add to it. So what this does is that you get a vertical translation. So you're moving it either up or down. So that's what this plus c does. And you can think about it too, like you're shifting all the y values up by c, right? You're increasing them by c. So that means like the whole graph will shift up by c. So it makes sense. But there are two cases. So if c is greater than 0, the graph will shift up. So for example, if you have c is equal to 2, you would call it a vertical shift 2 units up. So that's how you call it for c equal to 2. So you have vertical shift 2 units up, right? Yeah, use the term vertical shift. And then if c is smaller than 0, you would imagine it to go down. So the graph would shift down. Example would be c equals -5. You would say vertical shift 5 units down. You don't say like -5 units down or -5 units up. You use the absolute value of it. So like the positive form of it. So vertical shift 5 units down. That's how you'd say that. Let's look at the next part. So instead of c having c on the outside of the function, we have it as part of the input of the function. So here we have f, and its input is x minus c. Now this results in a horizontal translation. So now you're moving left and right. Okay. So there are two test cases for this. There are two cases for this. So if c is greater than 0, so say you have like c equals 4, this will be f x minus 4, not x plus 4. So make sure you get that correct. So if c is bigger than 0, the graph would shift right. So c equals 0, you would have a horizontal shift 4 units to the right. And if c is smaller than 0, that's the next case, you have a shift going left. So if c is -1, this will be f at x plus 1, not x minus 1. Make sure you get that correct. So this will be f at x plus 1. You get a horizontal shift 1 unit to the left. All right. Are there any questions about this before I click the Desmos link? Just to show you guys like what it looks like. Any questions about how these work? Okay, if there are no questions, get to the Desmos link. So I click on it. You guys should be able to see it right now. It's loading, actually. All right. I know it's a bit of a mess, but let's decompress it. So we have this base function, y equals x squared. That's your base function. You don't have any coefficients. You don't have any numbers added to it. Let's look at the next example. So this blue graph right here. Y is equal to x squared minus 4. Let me scroll down. So you see that this graph is shifted down by 4 units, as you can see, because of -4. So it used to be right here, 0, 0, and you shift it down to 0, -4. So this sample point. So that shifted down by 4 units. Let's look at the next one. Y is equal to, in brackets, x minus 3, all that squared. So you see how this is shifted to the right 3 units from this red function. So originally you had 0, 0 right here. Next you have 3, 0. Yep, there you go. 3, 0. So you can see that the right shift is 3 units. And you can also combine these together with this purple function right here. You have y is equal to, in brackets, x plus 1, all that squared. And then after that, outside, you add 2 to it. So x plus 1 squared plus 2. So, so this will result in a horizontal shift of 1 unit to the left because of this plus 1. So there's 1 unit left. The plus 2 makes it go up by 2 units. And you can see right here. So that point is 0, 0. This point is -1, 2. So you went left by 1 to get -1. You went up by 2 to get the 2, the y value right here. All right. So that's how those translations work. Are there any questions? All right, if there are no questions, let's move on to the next point. So that was translations. Now let's look at dilations, or like changes in size, right? So here's the first case of a dilation. So you have c times f at x. So c is your coefficient of the f at x function, f function. So function f, right? So this would result in a vertical dilation. So you're either stretching, or this means that you're stretching your graph up, or you're compressing it down. So that's what vertical dilation is. So say if you had a c that's greater than 1, so c bigger than 1, the graph would stretch vertically. So for example, you have c is equal to 2. So you have 2 times f at x. You would have a vertical stretch by a factor of 2. That's how you say it. That's how you phrase this dilation. You would say vertical stretch by a factor of 2. C is equal to 2. Okay, so that's case 1. What if c is between 0 and 1? What if it's a fraction? This means that the graph would compress downwards. So for example, you have c is equal to a fifth, 1/5, 1 over 5. This will result in a vertical compression by a factor of 5. So we don't say compression by a factor of 1/5. We use its reciprocal. So compression by a factor of 5. Yeah, for c equal to, you can also say vertical compression by a factor of 1/2, but we prefer using like integers instead of fractions. So we say vertical stretch by a factor of 2 for this one, and this one we say compression by factor of 5. Okay, that's c f x. Now in the second case, we have c inside the input, like as before right here. So we have c inside with x. So we have f at c times x of cx. Oh yeah, and for both of these, c cannot be equal to 0. And also put that c cannot be equal to 1, or else it would just be equal to its original function, right? So this will result in a horizontal dilation. So either stretching it outwards or compressing it inwards. So if you have c's bigger than 1, the graph would compress inward like this. So for example, you have c is equal to 4. With that, you'll have a horizontal compression by a factor of 4. So I phrase it, horizontal compression by a factor of 4. Now, if c is between 0 and 1, you will have the graph stretch outward like this, going out. And this is an example, you have c is equal to a third. If c is equal to 1/3, you'd say horizontal stretch, not compression. This is horizontal stretch by a factor of 3. Remember, we use a reciprocal for this c, so we get factor of 3 instead of factor of 1/3. All right. Are there any questions about this slide? And also provide decimal link. Any questions about dilations? Oh, Aiden has a question. So would you say a vertical compression of, is that 11 over 4? What you said? Not sure what you mean. Oh, so if you have c is equal to 4 over 11 or something? Yeah. So if you have c is equal to 4 over 11, you would say vertical compression by a factor of 11 over 4. Yeah. C can be, yeah, you can do that. Or you can just say, no, it's fine. Yeah, it's between 0 and 1. I mean, you can also say a vertical stretch by a factor of 4 of 11, but we usually want to have, I said integers, but you usually want to have a number that's bigger than 1 for this case. All right, that's what I meant. Interesting indeed. Let's look at the Desmos link, if you guys don't have any questions so far. It's always good to like graph these out, so just let you guys really understand like how these transformations actually work. Oh, I didn't type in anything. That's a bummer. Okay, here, I'll do a quick example. X squared, actually. So I'm not sure why my graphs got deleted. I'll do it quickly right now. right, here you go. Oh, I'm not sure why this one's red. Okay, can't change those colors, unfortunately. Okay, so this y equals x squared, that's the base function. This is your base function right here. It's a bolded red line. That's y equals x squared. Look at y equals 3x squared. It's the inner red line. Sorry, the inner red graph. You can see that it's you can't really see it like right now, but like you can see that it's kind of stretched out like upwards because of the 3. The 3 is in front of the x squared. So you see it's kind of stretched out. You can see like all the y values at any point are bigger than x values at any point. So say you have, look, negative 2, 4, that was for the original function. You should get negative 2, 12. You can see there. There. Negative 2, 12 for the 3x squared function. So you see the y values make it, the bigger y values make it stretch out upward. Let's look at this one. So y is equal to, in brackets, 1/2 x, all that squared. So this was a case of f at cx, right? So we have 1/2 x. So the 1/2 would make it stretch out horizontally, stretch out outward. And you can see from this graph right here, it is indeed stretched out horizontally, like so. It's and then if you take like any y value at any point, so you have here negative 2, 1. So that's for the 1/2 x squared function. This is negative 2, 1. For the x squared function, you have negative 2, 4. So you can see that the y values are smaller and that the graph is stretched out horizontally. All right. Any questions about this? All right, there are no questions. Let's move on to reflections. This one's probably easier to understand. All right. So you have negative f at x, so the negative's outside the function. This will result in a reflection of the x-axis. So you look at this diagram right here. So you see there's a parabola right here. If you reflect it using negative f at x, you get this reflected parabola right here, downwards. All right, so that's negative f at x. What about f at negative x? This will result in a reflection of the y-axis instead, the y-axis. So take a look at this graph right here. You originally had your function, so take the yellow dash. This was your original function. If you reflect it off the y-axis, you get it over here on the left side instead of the right side. All right, so that's pretty straightforward. Let's look at Desmos. So here I use the graph of square root of x. So this is your base function, y is equal to square root of x. So it's not x squared anymore, square root of x. And it's this green graph right here. If you've never seen it before, it's kind of like if you reflected a parabola, like 9 degrees to the right, clockwise. That's how the square root of x looks like. But yeah, so that's a green function. Let's look at the purple function. You can see that it's reflected off the x-axis. So x-axis is the horizontal axis, remember that? And so this is reflected, I guess you could say reflected vertically instead of horizontally. But yeah, you can see that the x-axis basically forms a mirror. It's like your axis of reflection. And this is what your reflected function looks like. It's this purple graph. It's reflected off the x-axis. All right. Now your black function, so this is y is equal to square root of negative x. You can see that it's reflected off the y-axis this time. So the y-axis acts as your axis of symmetry. And you see right there, it's on the left side now instead of the right side as usual. All right, are there any questions about this? Any questions about reflections? Yes, oh, nice indeed. Okay, if there are no questions, let's move on to the next slide. So now how do we combine everything? So we learned about, translations, dilations, and reflections. We can combine them together as well. But like, how do we do that? So first thing you have to know is that each of these transformations actually take priority. So the priority in order is that you have reflections, then you have your dilations, and then you have your translations. So from your base function, if you have a reflection, you first reflect it. Don't do translation first, otherwise that'll mess things up. So first reflect it, and then you can dilate it, and finally you translate it. So you move it left, right, up, or down. All right, so here's an example function of, so this is y is equal to -2 times f. So f is your function, actually. You can say y is equal to f at x. That happens a lot. So you can say that. So here's your function. You have -2 times f. And inside the function, you have 5 times x minus 10. Let me space out everything so it's a bit more clear. Change these to square brackets. Okay, so it should be more clear. So we have in your input, you have 5 times x minus 10. That's your input for f. And f is multiplied by -2, as you can see. That's the coefficient. And then finally, you add 1 to the whole thing. So how do we decompress this? So first, you want to find if there are any reflections, okay? First, look at the reflections. Like, find the negative signs. You can see that there's a negative sign in front of this 2. Basically, it's also in front of the f, the function, right? So this negative is in front of the function. That means you have a reflection of the x-axis. And you have to do this first. You state it first, like this. So reflection of the x-axis, that's the first thing you put down. Next, we look at dilations, right? So we have a 2 in front of this f, and we also have a 5 inside of the function's input. So the 2 and the 5 here would give you your dilations. So we can look at 2 first or look at 5 first. Usually you like to look at the 2 first. Sorry, like wherever's in front of the f first. So you get a vertical stretch by a factor of 2. That's what this 2 does. Stretches it vertically by 2. Now the 5, you'd get a horizontal compression by a factor of 5. So the 5 would compress it like this. That's what the 5 does. Now let's look at our translations. That's our final thing. The translations would be caused by this +1 here, and also this -10 over here. Also, just to note that you have 5 times x minus 10, you do not expand that. You want to keep it in factored form. And your horizontal translation would be whatever is inside the brackets. So you want to factor out the x coefficient always when you want to find your horizontal shift. So here your vertical shift would be 1 unit up. That's usually easier to look at. Your vertical shift is whatever is outside of the function. So it's just 1 unit up right here. Your horizontal shift would be whatever's inside here. So you have x minus 10. So that means your horizontal shift would be 10 units to the right. Not left, but the right. All right. Any questions about this? So that's how you combine everything. Any questions? Hopefully you understand how to phrase these, because we're going to use that in the next couple questions. All right. So let's look at these problems. So describe the transformations to get each of the following functions from their base functions. All right. So I have question 1, you have also question 2, and question 3. I'll give you guys a minute to figure this out, and we'll take it out. Okay, I think we're a bit short on time, so let's just take everything up. All right. Instead of having you guys like say, oh, I'll just take it up on the whiteboard. So what was our first function? It was this. Wait. Oh, how do I scroll down? I'm still trying to get used to this. Okay, we can only do this. Just zoom out. I'll write on it. Okay, over here. First function. It was this. So you have 2 times x minus 18. All right, we're going to type out the translations then. Not sure why the size is really small. Oh. All right. So if you want to find out all the transformations, so first we look at reflections. So see any negative signs? We don't see any negative signs right here. So it means we can ignore the reflections. Now we move on to dilations. Do you see any dilations? Of course. We see that there's a 2 in front of this x minus 18 squared. Also, I should write down the base function so you guys understand what it is. Like how to find the transformations. So base function for this one would just be x squared. So you have x, even though it's like x minus 18 squared, once you square it out, you would get an x squared. So that's your base function. All right, where is the text? All right, so you have a dilation that's caused by this 2. So this 2, basically you multiply in front of the x squared. So this means that you would get a vertical stretch by a factor of 2. Right, so that is your dilation. That's your vertical dilation. You're multiplying this 2 in front of this x squared. So it would just be this. Whoops. Basically, you're doing this. You have y is equal to 2 times f of x. That's what this 2 is doing. So yeah, you have this, but then you also have this minus 18 inside the brackets. So instead of this 2x squared, you have x minus 18 squared. And so you're basically substituting this x minus 18 into this x. So that means we can write the function like this, and it'll be easier to, when you write it in this function notation, it'll be easier to like visualize the actual like transformations that happen. No, I'm not sure why this text is getting smaller. There you go. Okay. So this minus 18, this will be a horizontal translation. So you'd write horizontal shift. And this is 18 units to the right. It's minus x minus 18. Right. So these are actually your only formations for this function f of x. All right. So that's question 1. Let's look at question 2. Let me write down right here. Alrighty. So first you want to figure out, usually you want to figure out the base function first. Let's write that down. You have an x cubed here, so that's your base function. Like whatever your highest degree is in the polynomial, that would be your base function. So yeah, x cubed is your base function. So you want to first figure out if there are reflections, right? You can see that there's negative in front of the x cubed. So that means that you would have a vertical, you would have a reflection off the x-axis if it's in front of the x cubed. I mean, this also means that actually, yeah, reflecting it off the x-axis or reflecting it off the y-axis doesn't really matter. Yeah, because it'll work both ways if you visualize it graphically. But let's use the x-axis. So we have reflection off the x-axis. That's how you would say it. All right, so we looked at reflections. That's all there is. Let's look at dilations. We don't see any like coefficients, right? Even though there's this 2 right here, that's not a coefficient. And the coefficient around here is like, if you ignore a negative, it's 1. So we can ignore that. So there are no dilations. Now, translations. Remember, we have this minus 2 right here. If so, it's outside of the function. So you have f of x minus 2. This means that you have a vertical translation. We'll call it vertical shift. This is a vertical shift. And since it's negative 2, you go down by 2 units. 2 units down. How you say that. And you further write the function notation, it'll look like this. So you have negative f of x minus 2. There you go. That's what it'll look like. So that's the second question. Now let's look at the last question. This one's a bit more tricky. Let's see. So we have a times negative b of x minus 6b plus c. So the square root ends here. So plus c is outside the square root. So your base function here would just be square root of x. So you remember to look at your x and like, where is it? You know, that will give you your base function. So this is just square root of x as your base function. All right. Oh, okay, move this around. There you go. So y equals x, square root of x is your base function. All right. So now let's look at all the, the transformations. First, let's look at reflections. You can see that there's a negative in front of this x. It's negative b, but like this negative results in it's a horizontal. Sorry, yeah, it's a reflection off the y-axis because it's inside the function. So you'd have this y is equal to we have negative bx, right? Let's write the whole thing actually. Negative bx minus 6b. So you're substituting this into the square root, right? But because of this negative, that means you have a reflection. It ends off the y-axis this time. Let's write down reflection off the y-axis. And there are no other negatives outside of that. So that's the only reflection we have. Now let's look at dilations. This one might be a bit more tricky. So a more obvious one would be this a. So a is in front of the function. So let's write that down. So we have a right here. So this, oops, that looks like a. But you have a in front of the f. So this means that what you'd get is you would get a vertical stretch by a factor of a. You can also say vertical like compression by a factor of 1 over a, but usually for like variables, we just say like stretch by a factor of that variable. Next thing to look at is the b right here. So see the b. So I mean it's in front of the x, but it's inside the function. So that means that you have a horizontal compression by a factor of b. That's how you'd say that. And those are the only dilations you have. Now let's look at translation. So shifting up, left, up, down, left, or right. Let's look at those. More obvious one would be this plus c outside. So it's outside of the entire function. So let's put it right here. So it's plus c. Okay, I guess I have to type of this. Oh, sorry, I'm still trying to figure things out. Size, there you go. Not sure why it's decreasing the size every time. It's a bit weird. Okay, so we have the plus c. The plus c would give us a vertical shift, right? Because outside the function, there's a vertical shift up c units. Well, we say c units up. Now, what about the horizontal shift? This is a bit more tricky. What you have to do, remember when I told you that you have to factor out the coefficient in front of the x? Well, you have to do that right here. So let's do that. So you factor out a negative b. Like even doesn't like factor completely, you still have to factor out everything that's in front of the x. But in this case, it factors perfectly. So you have a negative b times x plus 6. 6 times negative b would give you negative 6b. So that's how you factor it. Oh, I'm not sure why it's moving up. Okay, sorry about that. Right C here. Okay. So now you have your horizontal translation. You can see that it's 6 units to the left now. So let's do that. Okay. I'm not sure why the size is decreasing. Sorry about that. Okay. So let's write that right here. Horizontal shift 6 units to the left. So you can see right here, you have x plus 6. So this plus 6 means you're going left 6 units. All right. So that's the answer to that question, the third question. And that was the last one on that slide. Are there any questions about this whole thing? All right, if there are no questions, let's move on. A bit short on time. That's okay. Now let's look at something called exponential functions. So you've seen polynomial equations like y is equal to x squared plus x plus 1. In this case, the variables have constant exponents, right? So this x has an exponent of 2. This x has an exponent of 1. Although this is a constant, you say that it has like an exponent of 0, right? X to 0 would give you 1. But what if the variable was the exponent? What if the variable was the exponent itself? Instead of you have x in here, you have x as the exponent right here. Well, there is such a thing. You call these exponential functions. They look like this. So you have f of x is equal to a to the exponent x. So that's what an exponential function is. You have the x inside the exponent. So exponential functions, they're like functions in the form of this. And then a, there are some restrictions. You have a has to be greater than 0, but a cannot be equal to 1. If a is equal to 1, then the whole thing would just be a straight line where like y is equal to 1. And so that's not an exponential function. And the domain for an exponential function is that x belongs to a set of real numbers. And then your range for this exponential function is that y has to be greater than 0 and belongs to a set of real numbers. So let's look at this graphically, why the range is like that. So you can see domain x can be anything. So that's why x belongs to a set of real numbers. X can be any x value. But if you see that y, this never touches x equals 0. So like y equals 0. It's basically approaching it, as you can see right here. But it'll never touch it, right? So like there's no solution to like 2 to the exponent x is equal to 0. You can't get an exponent for x such that like you make that equal to 0. So it's why it never approaches y is equal to 0. And you can also see that it never becomes negative, right? If you take exponent of a positive number, it'll always be a positive number. So it can't be a negative number. So it means you have this, that's why you have this y is bigger than 0 restriction. But then you also still have to state that y belongs to a set of real numbers because y can be any positive number. Right? And we can look at special cases for a. So this is a between 0 and 1. Instead of having the graph look like this, where you have it increasing from left to right, you have it decreasing from left to right. So you have a high point on the left side, and then you just decrease, go down on the right side right there. That is a between 0 and 1. So say you have like y is equal to, oh, this thing is blocking it. I hate that. Say you have y is equal to like f of x is equal to 0.5 to exponent x. You would get this graph. And for a that's bigger than 1, you would get this normal graph, just like that. You're decreasing, you have small values on the left, but then you have really big values on the right. So then you have f of x is equal to 2 to exponent x. Any questions about this exponential functions? Hopefully there are no questions. I'm going to move on. A bit short on time. Now let's look at transformations for exponential functions. So your base function will look like a to exponent x. So a would change depending on like what your base is, right? A is your base. So domain for exponential functions would never change, but the range can change from transformations. So let's look at an example of this. So we have f of x is equal to -2 times 3, and then this 3 is taken to exponent of x minus 2, and then plus 5 at the end. So your base function will just be 3 to exponent x. Right? Your base is, so a would be equal to 3, and your base function would just be 3 to exponent x. So if you want to look at the transformations for this, you see first you look at the reflections. Reflections, you have a negative in front of the 3 to exponent x, so you have a reflection of the x-axis. So you're flipping it from here to here. Then you also have a look at dilations. First, you have a vertical stretch by a factor of 2, because you have this 2 right here. This 2 because you have vertical stretch. And there's no horizontal stretches at all, right? They would be in this exponent right here. If you want a horizontal stretch, they would be in this exponent, but there are none. There's nothing in front of the x right here. So you don't have any horizontal compressions or stretches. Next, you look at translations. You have this plus 5 outside of all that. So you got a vertical shift of 5. You have a vertical shift up 5 units up. And then finally, in your exponent, you look at for horizontal translations. So here you have x minus 2. That will give you a horizontal shift of 2 units to the right. All right. So you can see that this is the actual graph for this function. So you can see that the x value can be anything. Like, although you can't see like the x is beyond like 5, you can see that there'll still be a value for 5. It'll just be like a really, really small number, very negative number if you extended this. So yeah, x can be anything, but now you see the range is different, right? So now look at this graph. It's crossing the x-axis, so it can equal 0 now, and it can also be negative numbers. So it's not what it was before of y is bigger than 0. You can see that this graph is approaching this 5 value, so this plus 5, because of this. This is approaching 5, but it's never going to touch it. If you try to solve for this equation, you'll never solve for this is equal to 5. It's just impossible. So this graph will never touch 5, but it's getting really, really close to it, to the left side. And everything else is underneath that. So it can't be anything greater than 5. So you have your new range of y, such that y is smaller than 5, and y still belongs to a set of real numbers. All right? Any questions about this?